Yeah, good morning. I would like to show you how to simulate a simple bypass problem that is normally encountered in our chemical process calculations. Probably most of you would have solved this problem while dealing with the course on process calculations. Now the process is something like this. 1000 kg per hour containing 30% KOH solution need to be concentrated to a product containing 40% KOH solution. To do this, part of the feed is bypassing the evaporator. In the evaporator, the KOH solution is concentrated to 60% KOH by evaporating water, and the concentrate and the bypass are mixed together to give rise to the desired product with 40% KOH solution. Now, if you try to propose a mass balance, the overall balance, the KOH is entering through the feed and it is leaving the process only through the product. So 1000 into 0.3 should be equal to P into 0.4. So that gives rise to P is equal to 750 kg per hour. Now, similarly, if I try to make a mass balance across the mixer, I'll be able to say the bypass plus concentrate should be equal to the product, which is equal to 750. Then write a balance for KOH because we know the concentrations of KOH in all the three streams. 30% KOH in bypass, so 0.3B plus 0.6C should be equal to 750 into 0.4. Now, based on this, we'll be able to, solving these two equations, we'll be able to calculate B and C. Now, the point of interest here is, how do we simulate this problem using Aspen? So, let me define or demonstrate solving this problem in Aspen. So, the two components we are going to handle happen to be KOH and water. So, after choosing the components, choose the property model. Because we are interested in performing only mass balance, I'll be choosing ideal, for example, because the property model will not affect the mass balance calculation. Having chosen the property model and the components, you should be able to go into simulation. Now, the feed now is divided into two parts. One part is bypassing the evaporator, the other is going through the evaporator. Now, I will be modeling the evaporator as some kind of a component separator because we are only trying to remove some amount of water in order to concentrate the feed solution into 60% KOH. Now, the bypass and the concentrate are mixed together to give rise to the desired composition of KOH in the product. Now let us connect the input and output streams. This is the feed stream. Part of this feed is entering into the evaporator, and the remaining part is going through. Of course, we are removing water vapor, and the concentrate is mixed with the bypass to give rise to the desired product. And this is your product stream. So for convenience, let me rename these streams. This is the feed stream. This is the bypass. This is the product. And this is the concentrate. So let us now specify the inputs. Remember, we don't know how much of the feed is bypassing the evaporator. So how much should be bypassed is dictated by the product concentration, the desired product concentration of 40% KOH. And whatever may be that is entering into the evaporator need to be concentrated to 60% KOH. So depending on the amount of S2 that is entering into the evaporator, we need to remove corresponding quantity of water vapor in order to bring the concentration to 60% KOH in the concentrated solution. So these are the two issues involved in this problem. So let us go ahead and try to define the problem. As I said, we are dealing with only mass balance. So temperature and pressure will not have any effect. So the mass flow is 1000 kg per hour. This contains 30% KOH and the remaining is water. This is given in the problem statement. So we have defined the feed stream. Go to the next step. Now we are trying to talk about the split fraction. How much need to be bypassed? We don't have any idea. So let me assume about 25% of the feed is bypassing the evaporator, just as an initial guess. We will try to resolve this problem later. Next. So we are now looking at the component separator. So let me look at this. S3 represents the water. Let me rename it also for convenience. So we are trying to remove some quantity of water such that the concentrated solution contains 60% KOH. So look at this. I am defining this with respect to water. So this water stream should not allow any KOH, but we don't know how much water need to be removed. Again, let me assume 50% of water that is entering into the evaporator is removed in the water vapor stream. So the remaining solution will be concentrated. We don't know whether it will correspond to 60% KOH or not. Go to the next. These are the two assumptions we made. We assume that 25% is bypassed, and we, after removing 50%, we would like to see what is the concentration of KOH in the concentrated solution. Of course, these two need to be resolved. I think you all know the kind of problem that we are dealing with. So for example, if you look at the product, the mass fractions. So we got to a mass fraction of about 40%, roughly the required solution, and the concentration of concentrated solution is about 46%. Now we need this to be 60%, and we need the concentration of KOH in the product to be 0.4. So remember, the problem is all the models that you are able to use, most of the models that you are able to use in any simulator will be able to do only rating calculations. So as a result, we have this kind of a problem. So let me resolve this problem by using a design spec. So first of all, I'll try to define a design spec on this. Irrespective of the quantity of the solution that is entering into the evaporator, I would like to make sure that the concentrated solution will have 60% KOH and the corresponding quantity of water need to be removed. So I'll try to deal with this by using this design specification. So what is that we require? The concentration of KOH in the concentrate. This is a stream variable. It is mass fraction. Stream is concentrate. Component is KOH. We know the spec. We wanted this to be at 60%. So I want this to be at 60% irrespective of the quantity of solution that is entering into the evaporator. Provide some tolerance. In order to do this, what we need to vary, because we don't know how much solution is entering. In order to make it into 60%, we need to remove certain quantity of water. So I'll be varying the quantity of water that is going to be removed. It's a block variable. Block is B2. It is B2, right? This is B2. Then variable is flow fraction with respect to water. So we assume 50% is going to be removed. So let me vary this from 0.1 to 0.9. We don't know where it would be. So in order to meet the concentration of KOH solution in the concentrate, we are trying to vary So we made a small mistake probably. We are defining this with respect to we wanted to remove the water. So we got to the required solution. Let us look at the results of the design spec. When we removed 0.5, we were able to concentrate the KOH to 46%. But when 71% of the water is removed, we will be able to reach 60%. Of course, this is based on 75%. 750 kg is passing through the evaporator. But we don't know whether this would be required or not, because there is another requirement for us. So we were able to achieve 60% concentration in the concentrate, but we did not get the required concentration of the product. So in order to manage with this, let me use another design spec. So this is product concentration of KOH in the product stream. So this is also a stream variable. Mass fraction, stream is product, component is KOH. What is our requirement? It should be at 0.4. Use some tolerance. What is that you are trying to vary? The amount that is getting bypassed in the splitter. So block initially we assume this as 0.25. The block B1 represents the splitter, lower fraction with respect to bypass. So we don't know how much need to be bypassing. So I change from 0.1 to maybe 0.9. So remember, both these design specs will be interactive in nature. Once you change the bypass, the amount that is getting into the evaporator changes. Accordingly, it has to adjust the amount of water that need to be removed in order to make the concentrate to 60% KOH. Right? Similarly, depending on the quantity, once you mix the quantity of the concentrated acid and bypass, we need to get the concentration of the product at 0.4. So let us look at the results. Okay, otherwise I'll see like this. So you can see the concentration of the product now is at 40%, like what we wanted. Similarly, if you try to look at what is the concentration of the concentrated KOH solution, so this should be at 60%. So we got to the required 60%. And what we are interested, the quantity of bypass. Now the bypass is about 501. The small difference is probably because of our tolerance. Of course, if you make it stiffer, you will be able to get to the right result, which is equal to your analytical solution. As we have seen, the analytical solution gave us a value of 500 and 250. So this is how you will be able to manage with simulating a bypass problem.